In this example, we're going to draw the deformed shape of the frame shown, and we're going to do this without the benefit of having a moment diagram. What I'm showing here is the frame pinned at both ends, L-shaped frame, uniform load across the top beam. These are just two segments where I'm going to draw first a trial shape that we'll get wrong, and then the correct trial shape. Once I have that, I'm going to look over here and I'm going to sketch out the moment diagram that's implied by that trial shape. Let's start. We have a couple pieces of information here. One is boundary conditions at each of the pins, and since we assume that frame members don't stretch, we also know that this point has to stay right there. I'm going to start by saying that, listen, here's a uniform load, it's pushing down, so somewhere here the middle of the beam needs to be pushed downward. So I'm going to sketch a little smooth shape through here. This little point's distracting at this point. I'll erase it. I know that that I need a right angle here, so I'll make sure that I respect a right angle at that joint, and I'll continue downward here. I'm gonna just darken this a little bit. So here's my first trial shape. And let's evaluate. I've accounted for the boundary conditions. I have accounted for the continuity of angle. I'm not allowing that angle to change. I don't really know if I've gotten my curvatures right. I have nothing else to reference it against. But I do need to look at joint equilibrium. And if I look at joint equilibrium, and actually I'm going to look at the adjoining members here. The horizontal member on the right hand side has upward curvature, which requires a moment like that, equal and opposite onto the joint. Looks like that. This vertical member has rightward curvature that requires that moment. Equal and opposite onto the joint, I have that reaction. And the problem that I've exposed here is that both of these moments are acting counterclockwise. So this joint, as I've drawn it in this shape, cannot be like that. That joint would not be in equilibrium, it would be spinning. So I have to fix something. And what I'm going to do is I'm going to allow this joint to relax a little bit. I'm going to make it so that it doesn't rotate quite so much. Now this is going to require some detail in the drawing. Certainly have to be careful with how I do this. So I'm still maintaining the right angle. I'm still showing a bit of a rotation. I'm still showing a bit of rightward curvature like that. But here I'm going to start by showing downward curvature, a point of inflection, and then upward curvature back in. So here, if I look at joint equilibrium in the other case, over here on the right hand side of that joint, I have downward curvature. Over here it's the same as before. What I notice in this sketch is that both of these moments point in opposite directions. That tells me that this joint is potentially in equilibrium. So what I've drawn here is now something that is physically consistent with equilibrium. To finish the problem, I'm going to draw the moment diagram that's implied by this deformed shape, just to see what it is and to see if anything strange comes out of it. I know that there's zero moment at a pin. Zero moment at a pin. And I actually know that there's zero moment right about here, because it's a point of inflection. I also know that because this is constant, my shear is linear, my moment will be parabolic. So I have a parabolic moment shape over here. To avoid a cluttered diagram, I'm going to draw it with negative moments on the top. And I know that these moments have to be the same magnitude here, so I'm going to draw them about the same. I'm going to go with a parabolic shape through the point of inflection. I know that this is downward curvature and upward curvature. On the column, I have zero distributed load, constant shear, linear moment. So I'm able to draw this right here. It is rightward curvature. You notice that both of these curvatures are consistent with the curvature that's implied here on these diagrams. So everything is looking pretty decent here. There's nothing that stands out as being out of the ordinary. So once again, we've drawn a deformed shape for this frame without the benefit of the moment diagram. We had to go through one step where we identified a problem with joint equilibrium. We fixed that problem. We rechecked joint equilibrium, and we then sketched out the moment diagram that was consistent with that. It looks pretty decent. Once you have a bit more experience, you'll recognize this as being the moment diagram that corresponds to a propped cantilever beam. If this were a fixed end over here, and there were a roller, and there were a uniform load, that's exactly what the moment diagram would look like. So we recognize this as something that we've seen elsewhere that makes sense. With that, the problem is finished.